In Calc 3, they talk about vectors and applications in a lot more detail. But in linear algebra, we're going to talk about it also. So you don't really need to know too much about vectors as described in Calc 3, but we need to establish a few things about vectors, and we're going to use them as a tool in linear algebra. So in Calc 3, it was really defined as well, at least the way I do it. I define a vector as just a point where it is something with a direction. It's a line segment. It's a directed line segment, so it's something with a direction and it has a magnitude. But I look at it as a point where the arrow would be drawn from the origin to that point, and that's how we would describe the vector. So as just an illustration, if we have the point 2, 1 here, then the vector is a line segment that has a direction and the magnitude, and by magnitude we mean length. This is your vector. To 1. There's a lot of different ways to write the vector, and for the sake of linear algebra in this class, we'll write a vector as a column vector. So it's essentially a matrix that only has one column and several rows. So the vectors that we're going to be dealing with are going to be 2 by 1, 3 by 1, or an n by 1 vector. So depending on how many rows we have, well, that's going to be the first number, and then we're always going to have a 1 column matrix. And so any 1 column matrix that we have, we can look at it as a vector. Okay. We could do this in 2 dimensions or 3 dimensions, and like it's implying here, we can do this in n dimensions, in any dimension that we want. And we'll see examples of these things. Now, visually, this vectors would make sense for us to view in 2 or 3 dimensions. Anything beyond that, we won't be able to view, so you're just going to have to use the theory behind vectors and matrices to work with 4 or 5 or 6 dimensional vector. Okay. Addition of vectors. By the way, the notation, if you already didn't see it, is going to be a vector, a letter with an arrow on top. In the textbook, it's boldface. So when I'm doing stuff, writing things by hand, it'll take a little bit too much trouble to boldface it. So we'll do the arrow on top to denote that it's a vector. And we do need to distinguish between a vector and something that's not a vector, so that when we're working with things, we understand what we should expect. All right, vector addition. Let's say V and W are vectors, where V is equal to V1, V2, and W is equal to W1, W2. And notice the arrows on top of the name of the vector V and W, and notice the non-arrows inside of the 2 by 1 matrices that I have here, V1, V2, W1, W2. So when we add these 2 vectors, what we're going to get is another 2 by 1 vector that is essentially adding the components of those original vectors. That's easy enough to to figure out, yeah? So that's vector addition. And the other major operation that we're going to discuss is scalar multiplication. So the scalar multiplication, by the way, if something is not a vector, we tend to call it a scalar. So any real number that we're going to deal with, we're going to call it a scalar, just to give it a name. Yes? Oh, yeah, subtraction will be the same thing. Plus and minus. We could also look at subtraction as addition with scalar multiplication. So as we do the scalar multiplication, we'll see how that would work. So a scalar can be denoted by usually any letter, and a lot of times when they're dealing with vectors and scalars, they tend to use a Greek letter for a scalar, but that's not really that big of a deal. We can just use C or K or A, but we'll use alpha for the scalar and times a vector. And what happens here is that we take your vector and then we're going to multiply each element in that vector by the scalar. So with these two operations, addition and scalar multiplication, we're really not changing the size of the vector. And we're not changing the property of the vectors or anything like that. It's still going to be a 2 by 1 vector. And if you start off with a 5 by 1 vector, then addition and scalar multiplication will still work. What we do have to be careful about is that we cannot add a 2-dimensional vector and a 3-dimensional vector unless you assume certain things, like maybe one of the components is equal to 0 or something. But in general, we can't do additions of vectors in different spaces. Okay? Any questions? There is a parallelogram rule that's kind of related to addition, and that gives you a visual for the idea of addition. So if you have V and you have W, and the way to visualize this, you would put these two vectors with its tail in the same point. Then vectors, by the way, are things or line segments, essentially arrows with direction and magnitude, but the position of where they are in space doesn't matter. So we can do translation, like in this case, I just took W and I moved it up next to V, or I could take V and move it next to W. But geometrically, the sum of two vectors is a diagonal of the parallelogram spanned by those two vectors. And there's something else too. It turns out that geometrically, you can also view the difference between those two vectors. Whoops. And the difference between the two vectors turn out to be the other diagonal of your parallelogram. So this is the difference between the two vectors. Is this V minus W or W minus V? Do you guys know? For some people that might have taken this vector stuff before? Yeah? The question is, this vector that I'm pointing at currently in gray is the difference between the two vectors. My question is this V minus W Or is this W minus V? Yeah. W minus V? Agree? Do we all agree? It's not. It's V minus W. I don't know. What? Are people here taking physics? Have you taken physics? I think about it as head minus tail. So the head of the arrow is the point of the arrow, and then the tail of the arrow is the beginning of the arrow. So arrows can be described with head minus tail. Yes? Uh, Not necessarily, because we can move these things around a little bit, and it gets a little bit more confusing that way. We will deal with angles eventually, but would not apply so much here. What? Yeah, except that would be a lot more complicated. But that's a good visual also. So let's see if I could do this. V, and then instead of a W going this way, I'll put the W over here. So V, and then this is negative W. So it got scaled to go the other direction. And then now the parallelogram would be going this way. So we would add V plus negative W, which is the same thing as what we were looking at, right? It's the same vector. Well, if I did it right, it would be the same vector. That looks the same. I must have done it right. Okay. So that's the parallelogram for addition and actually subtraction. The length of the vector, if we look at the vector as, like I mentioned before, as a point, or a vector as a vector whose tail is at the origin and whose head is at the point that it's pointing at, then we can find the distance of this arrow, the length of this arrow. So the magnitude is like the distance. So the length is like the magnitude of your vector. And then we denote it by this, by a double bar. Now sometimes we use a single bar. What do you think of when you see a single bar? It's absolute value, right? What is the absolute value of a number? It's what? It's a distance from zero, so it's the length of the number from zero. So that's the same thing. And so sometimes I might get lazy and not put double bars, and I just put single bars, and you should automatically assume that that's the same thing as the length. And then the length from a point to the origin would be just each of the components minus the origin, which is 0, squared, and then all falls under square root. So this is for 2 dimensions, but we can imagine that we can find the length of a vector in any dimension by just kind of extending this idea of the distance between 2 points. Whether those 2 points being 2 dimensions, 3 dimensions, or 15 dimensions is going to be the same formula. Okay, questions? So these are some of the things that we could do with vectors. We can add, we can scalar multiply, and we got the geometry picture in our heads for addition and subtraction, and then we got the idea for length of the vector. By the way, the length of the vector is a vector or a scalar? It's a scalar. So results. The result for your length is a scalar. Addition and subtraction, and when we do multiplication, we did scalar multiplication, but we haven't really defined 2 vectors being multiplied to each other. That's because that idea is a little bit more complicated. And in a Cal3 class, for example, you might have 2 different kinds of multiplications. If anybody's taken it before, you might have heard of the dot product and the cross product. So in our class, we'll not deal with the cross product, but we will very much in detail deal with the dot product. And the dot product is sometimes called a scalar product, and so knowing what your result should be is important. You know, if you're doing some sort of operation, are you expecting a scalar or are you expecting a vector? So you should know these things ahead of time so you can anticipate what your answer should be. Any questions? All right. So there's a lot of properties for vectors. I don't know why the 0 vector is in this. Maybe this should be different. Let me add this on to our notes. A vector whose entries are all zeros, called a 0 vector, is denoted by, this is the wrong notation, it's denoted by 0, either boldface 0 or 0 with an arrow on top. So just like with vectors and scalars, we want to distinguish between them. If we're talking about zeros, we want to distinguish between a 0 vector and a 0 scalar. So if you see a 0, just plain 0 by itself, then you can imagine that's the number 0. But if you see a 0 with a vector on it, or a vector arrow on top, then you would have to assume that this is some sort of 0 vector. And you should be able to, hopefully from the context of the problem or the thing that you're looking at, would be able to tell what dimension that you're working with. So a 0 vector is a vector full of zeros. All right, so next is a set of some algebraic properties for vectors. If we want to get all fancy, we can give some of these properties names. We have the addition is commutative. When you switch the orders, it's called commutative. The addition is also associative. Now, when we add a 0 vector to something, I guess this should also have a result that this is equal to u. So when we add a 0 vector to a vector then you're going to get the original vector. So that's another, important property that we should already know of, or at least kind of relate to property. This is called an additive identity property. And identity is 0. And then you can also have something where you can start off with a vector and you can add another vector to it to get 0, and that vector does exist, and that's called the inverse or additive. Additive inverse. In this case, we know it to be the negative just by multiplying it by a negative sign, and we kind of call that the opposite. I don't know if that's necessary. Or the negative. Okay. Now there's a distributive property, but the distribution isn't a vector distributing to another sum of vectors. It's a scalar distributing. So it's a scalar distributive, and you can distribute the scalar or distribute the vectors. So those are those two properties. So there's a scalar distribution, and then there's associativity with a scalar also. And then there's a scalar identity, which is the same as our regular scalar, I should say, scalar multiplicative identity. And that is to say, if you multiply it by 1, then it's not going to change. Okay. So these are a handful of properties. Now, this is really, really important when you're doing proofs. We're not going to do that much proving in this class. If you're a math major, you should be sad that we're not doing that much proving in this class. But everybody else would probably be happy. But we will do a little bit. So we will call on these list of properties, not just these vectors, but when we get to matrices, the matrices are going to have properties as well. And we will need to call on some of these properties to be able to prove certain things. Questions? All right. So this is where it's going to be, some of this vocabulary will be important for us from now until the end of the semester. And this is one of them, one of the important terms that we'll be using a lot. Linear combination. So when we talk about linear combination, we generally think of a set of vectors. So a linear combination of a set of vectors is going to be a scalar multiple and sum of all those vectors. So we're going to take a vector, scale it, and add another vector and scale it. And remember, these scalars are just any real number, so they could well be 0, or most of them. But the idea is that we have a set of scalars and a set of vectors that we're multiplying, and then we're going to add them all up together. And that idea gives a linear combination. So they give the scalars a special name. They call it weights. It's not going to be that big of a deal, but sometimes we need to refer to these scalars that we come up with in our linear combination. So they're going to be called weights. Okay. Any questions? So either you guys really, really understand this, like totally, or you guys are just bored and can't even engage the question. So maybe I'll try to give you guys some work to do next time in class where you guys are moving around and talking and stuff like that. All right, linear combination of a set of vectors. What else? Vector equations. Yes. Well, the vector itself is not a linear combination. It's the set of vectors that you have would be a linear combination. So the easiest thing I can think of is we can go in 2 or 3 dimensions. Are you guys okay with dealing with 3 dimensions? Okay, let's deal with 3 dimensions and let's come up with a simple example of what it means to have a linear combination of something. Thanks, Pat, for asking the question. So now we can take a look at a point in 3 dimensions. Let 2 comma minus 3 comma 7 be a point or a vector in 3 dimensions. Now also in 3D, we have the vectors I, J, K. Now, are we familiar with the I, J, K vectors in 3 dimensions? So the I, J, K vectors are called the standard basis vectors for 3D, and the I vector is 1, 0, 0. The J vector is 0, 1, 0, and the K vector is 0, 0, 1. So I'm going to focus on the I, J, K vectors and say, can I write the I, J, K vectors as a linear combination so that I can get to this point 2 minus 3, 7? Does that question make sense? Okay, if that question makes sense, then that's what linear combination is. So it turns out that, and I'm going to switch notations on you because I want you to feel comfortable about switching notations. So the 2 minus 3, 7 vector, which I'll now write as a column vector, can be written as some number times the I vector plus another number times the J vector plus another number times the K vector. And we know what these numbers should be, right? If we know the rules for addition and scalar multiplication, we can scale the I vector by 2, we can scale the J vector by -3, and we can scale the K vector by 7. And now if we do the scalar multiplication and addition, we're going to get exactly 2, -3, 7. So this expression we just wrote is a linear combination of I, J, K. And the numbers 2, -3, 7 are the weights. Okay? The red numbers are the weights. And this whole expression that's underlined in black is, oh, you guys can see the colors today. Erica. So this whole thing is a vector, yeah. And and I want us to be comfortable about dealing with points and vectors and interchanging those ideas. So if we have a vector, you can imagine that vector as a point, and then the vector would be from 0, 0, 0 to that point, if you want to visualize it. Yeah, so if you imagine 2, -3, 7 as a point in 3 dimensions, and you draw a line from the origin to that point, then that's your vector. Because I really want to just do that in Calc 3, and since I do that all the time in Calc 3, I'll do it here too. So in this class, we sometimes look at these vectors as points also, but sometimes, because especially when we go to Rn and we can't visualize it anymore, we want to be general about it. Matt? Oh, we'll figure that out later. Yeah. So later on, we're going to talk about these ideas called linear independence and span. Oh, we might talk about span now, but we'll talk about those ideas, and then so there might be a time where we have a set of vectors, and we want to see if we can write another vector as a linear combination of these vectors, and we may be able to do it, we may not be able to do it, and that's what we're going to do. Maybe in the next page. Okay. All right, so I think there's one more idea before we get to that, and that is called a vector equation. So what we're interested in doing is we're going to translate some of the things that we're dealing with matrices into, I think there's more stuff to talk about on this page, but let's see what this says. A vector equation, x times a, and a is a vector, x is not a vector. So look at the boldface. Since this was done on the computer, then we just boldfaced it instead of using the arrow. X1 times a plus x2 times a2 plus all the way up to xn has the same solution as a linear system whose augmented matrix is this. Now remember that a1, a2, and all that stuff, those are all column vectors. So we could actually write these things as columns. In particular, B can be generated as a linear combination of A1, A2, up to AN, if and only if there exists a solution to the system corresponding to the matrix. What? Get all mathy on me. All right. Let's pick a really simple example, like the one, maybe an example that we did on the first day where we had nice numbers, like this one. And let's see how we can translate these ideas, because what they're saying is that we have a system of linear equations and the matrix, augmented matrix. Let's see how we can write this into the augmented matrix and see how we can write this as a system and all that. So what we're saying is that we can come up with a vector equation that mimics this system. That says exactly what the system is saying. So what they're saying is that I have an x1 times some vector plus x2 times another vector is equal to, in this case, we're only dealing with 2 dimensions. And then you can see that they're just the coefficients, right? That kind of makes sense. So x1, the first equation is being multiplied by 2, the second equation is being multiplied by 5. So we must be dealing with the vector 2, 5 for our A1, so to speak. And then 4, 7, and then negative 4, 11. All right. Now, if we could take these vectors, A1, in this case, this is A1 vector, A2 vector, and the B vector. If we take these three vectors and write them as a matrix, so this notation where they have A1, A2, dot, 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 A, and B, that's like putting those vectors and just putting them as columns of a matrix. And so this is your, quote, augmented matrix. Now we solved for this already. I don't want to go through the whole solution again. We solved for it already somewhere. Is this the one? Are you sure? But this is the right one? Okay. So we solved for this, right? And got 1, 0, 12, 0, 1, negative 7. So I'm going to skip all the steps and just go to that solution. See previous notes. So we're able to find a solution. We're able to find a solution that says x1, this is our pivot column in x1, x1 is equal to 12, and our pivot column here in x2 is equal to negative 7. And so we've essentially expressed our b vector, our negative 4, 11, as a linear combination of the other two vectors, 2, 5, and 4, 7. So let's write that in words. B vector can be expressed as a linear combination of A1 and A2. And the weights, if we're going to consider weights, are going to be 12 and negative 7. So our B vector, negative 4, 11, is equal to the linear combination is going to be 12 times 2, 5. So A1 is equal to 2, 5, and negative 7 times 4, 7. Okay, and the solution that we got are what we refer to as the weights in our linear combination. Okay, and those weights happen to be the same as the solution to the original system that we have. Question? All right. It's pretty. Oh, yeah. If there isn't a solution, then we have to say that we cannot write that vector as a linear combination of the other two vectors. Yeah. Infinitely many solutions, that's the other issue, right? We can either have no solution, exactly one, or infinitely many. So if you have infinitely many solutions, then, I don't know, then there must be something going on with those vectors, right? The vectors. Maybe we'll see an example of that today. Maybe there's some examples there. All right, maybe we'll come up with that example, but keep that in mind. So I should probably start this in a new page since this is pretty important, but I'm going to start it here anyways. So linear combination, that phrase needs to be something that we have to understand. We're going to use that phrase a lot. The other phrase that we're going to use, or word, or vocabulary phrase, word, is span. Okay, so now we have a span. If you have a set of vectors, then you can describe the span of those vectors as any linear combination of those vectors. A span of a set of vectors is the set of all linear combinations of those vectors. It's denoted by span, open brackets, list of vectors, close brackets. And they generate what we call a subset. Okay? All right. What? Yeah. I'm going to put it on the new page. All right. Let's take some examples. Let's for the sake of simplicity, let's stay in R2. R2. I have to write these things. So let's take a look at a span of only one vector. And for simplicity's sake, let's take a look at the span of only one vector in R2. And let's pick a nice easy vector like 1, 1. What is a span of 1, 1? Yeah. Just a line in R2. What? Well, it's the linear combination of the set of vectors that we have, but we only have one vector. So what is the set of linear combinations of this one vector? Yeah, so it's just scaling the vector, right? Is that what you're going to say? So it's like C1 or just C? Where C is just the real number. Could be 0, sure. Could be 1, could be 5, could be 7, could be -3, right? Could be anything. Yeah. Not only that, but Pedro said it's exactly the line, and then the line that passes through 1, 1, as a matter of fact. Yeah. Yeah, it's all the vectors that you can make out of that vector. Or in this case, that vector, but in general case, more vectors that you will, if you have more vectors. If it's not 1, 1, should we change it? Let's change it. We're still early enough, right? Okay. Change it to what? Go negative if you want. Whatever you want. So somebody took it away from you. 4 minus 6. Who said that? 4 minus 6. Okay, say we have 4 minus 6. So let's take a look at what this means to what is the span of this vector. So it looks like it's just a vector going to that point, right? So now what if I take that vector and I scale it by just some random number a? It will. So I have to zoom out a little bit, but if you imagine scaling it, right, I'm kind of restricted to just this line. I don't get out of that line. So that's the span, right? So what happens is that this thing is going to be any point on the line containing 0, 0, and 4, negative 6. For a line, we kind of have to define 2 points, right? And so 0, 0, and 4, negative 6. Yeah. Right. Right. Yeah. In our example, we only have one vector. In this example that we have, we only have one vector. Let's do another example where we have 2 vectors and see what happens. Okay, but that's what's happening now. That's why there's only one. We're kind of restricted. You can, but the vector, we're looking for the span of not the I and j vector, but we're actually looking for the span of the vector 4, 6 only. So if we come up with another example where we have 2 vectors, then we can change those 2 numbers in front of those 2 vectors. So let's still stay in our R2. Let's say we have a vector v1. Now I need 2 vectors. What is it? Okay, so the span is going to be all vectors where we multiply c1 times 1, 1, and then we add it to c2 times 4, negative 6, where c1 and c2 are some real number. scalar, I guess we call it. Okay, so just to think ahead a little bit, what do you think the span of these two vectors are in R2? The area between those two lines, okay? Any other? Yeah? The diagonal, okay?
Since we're adding the combination of those two together, it'd be would have been like the added vector.
Uh-huh, but what are those added vectors when you put them all together? That's the question, that's the span. Oh, let's start using our vocabulary. So what do you guys think? We have the parallelogram. The span seems like it would be the parallelogram or maybe just the diagonal. All right. So tell me what this, tell me what it means for, or here, let's go with Luis's comment first. Tell me about this vector that I just drew, something to do with a diagonal of parallelogram. Is that in the span of these two vectors? It certainly is, right? So this vector would be v1 plus v2, and yes, it's in the span. Okay, now tell me about anything in this parallelogram. So I'll randomly pick a point on this parallelogram, or should I say a vector, and is that vector in the span of this? So this is some vector that I think it's a times v1 plus b times v2 is in the span. What are A and B, you think? Well, if it was 1 and 1, then we would get exactly the diagonal. Let's throw a couple of guesses here. Approximately. For this green vector that I just drew. Yeah, so it'd be less than 1 for both. So let's say A is the one that's being multiplied by 1, 1. So let's say this is 1/2. And let's say it's 3/4 for multiplying by B. And so those are real numbers being multiplied to those vectors and being added. And so that looks like it'll be in the span. And everything in that parallelogram would certainly work. Is that all? We can have negative scalars also, right? Oh, and we can have numbers bigger than 1. So if we restrict our scalars, our weights, to be between 0 and 1, then we're stuck within that parallelogram. If we go negative, then we're looking at these numbers or these vectors here. If we go bigger than 1, then we're looking at these other ones. So you're gonna So here's a question. What happened? There it goes. Here's a question. What if you randomly pick another vector in 2 dimensions? Any 2 numbers? Yeah. Can we pick any 2 numbers? 5 and 1. I thought you were going to go big. 50 and 100. Anything, right? If we pick any number or any point or any vector, 5, 1, 50 and 100 up here, if we pick any vectors, can we write that vector as a linear combination of 1, 1 and 4, negative 6? Yes. We should be able to. So pick any number, I guess any vector R2, and then write as a linear combination of the 2 vectors that we're dealing with. So example would be 50 and 100. Can we write this as a linear combination of 1, 1 and 4, negative 6? And when we ask that question, we're actually taking ourselves back to a system of linear equations. We're really looking for weights, which are the 2 scalars, x1 and x2, that would make this equation true. Now we can do this in a couple of ways. We can go back and rewrite it as a system of linear equations, or we can move forward and write it as a matrix and see if we can reduce the row reduce the augmented matrix and get solutions that way. But you should be pretty much guaranteed. I don't know if anybody's jumping on this and going to give me the answer, but I don't want to solve for this. So let's change this to 5, 1. So x is equal to Is it going to work? What? It would be 1, 1 for this, for 5, 1? Oh, you going to say? 50? Oh, let's put 50 and 100 back. 70 and negative 5. Bam. So yes, we can write this. And we randomly chose that, not that, the randomness is we should be anything. So the idea is that we could put any number here, and that we can always find a linear combination of those 2 vectors. What does it say for the span? What can we conclude here? What is the span of those 2 vectors? And the span of those 2 vectors is all of R2. I want to go back to the span of the first example that we said. We didn't really say what the span is, but we'll talk about it in a minute after you guys say that you understand this example. Do you understand this example? All right. Yeah. We're playing with the idea of a span. We're we're trying to figure out what the span is. So if I have two vectors in R2, or these particular vectors here, they span everything. And what they mean by they span everything is that I could take any linear combination, and by linear combination I mean, something times the first vector, something times the second vector, and add it. And I can always find a solution for it. Yeah. Yes. Yes. Well, our first example is an example where the span is only a line. Well, the span is 4 minus 6. Is a line, or is the line. What's the equation to that line? 0, 0 to 4 minus 6. What's the slope? Minus 6/4. So the line that goes through 0, 0, and 4 minus 6. Is that right? Rise over run, 0, 0. Slope, change in x, change in y. Whatever. Yeah. Yeah. So our first example did not span the whole thing. It only spanned a line. Our second example spanned the whole thing. Yeah. And the number of vectors that we're talking about. Well, maybe we weren't quite finished with the two-dimensional story yet. Because I can give you two vectors in two dimensions that won't span the whole plane. Can somebody give me an example of two vectors in two dimensions that won't span the whole plane? Anybody except for Pedro. Andrew? Yeah. Okay, so 0 for the y components and any number for the x. Can you picture that? Just a horizontal line. Okay. Were you going to say something similar? Say it again. So my vectors 1, 1 and 2, 2 can't span the whole plane, right? Because they're going in the same direction. So any linear combination of these two, you would add them, you would still be within that line. So if I say those are my two vectors, and then I pick another vector that's not on that line, I'm not going to get a solution. Okay. All right. Span. So in 3 dimensions, if I have only one vector, then I'm guaranteed to span a line. Well, if I have two vectors, if they're the same vector or they're collinear, then I'm still going to span only a line. In 3 dimensions, if I have two vectors, then I would span not just the parallelogram spanned by those two, but the whole plane. And this is going more to Calc 3 now. If I have a span of two vectors that are not going in the same direction in R3, then not only am I talking about the parallelogram, because if I just talk about the parallelogram, then I'm letting my scalar, my weights to just be 0 and 1. But I want my weights to be anything. So they would span not just the parallelogram, but the whole plane. So that would be a plane in 3 dimensions. And if I have 3 vectors that are not all collinear, then that would span the whole space in R3. Because you can have a whole space in R5, but we won't talk about that yet. That's heavy, huh? Another way to think about spanning is that if you have the two vectors and imagine making a grid out of those two vectors. And by that, I mean we can start off with a line, 1, 1. How do I do a line? Oh, y equals x. So that's a line, right? And, well, this is probably going to take a little bit more time. Do I have time? I know, huh? Let's just get to it. All right. Maybe I should just. Nah, I'll need to have this a little bit more prepared. I can't do it off the top of my head. What I wanted to do is I wanted to make a grid of these vectors. And so by that, I mean, and these vectors are not really good vectors to do it because one of them is considerably longer than the other. But another way to think of spanning. Oh, I'm out of room already. Oh yeah, I'm sure there's an example in the book probably. So another example of spanning is to actually make a grid instead of having those square grids like we do for graph paper, like this square grid that they have here, for example. Instead of having a square grid, we have some sort of rectangular or parallelogram-ish kind of grid like this. To say that this is V1, I don't know which one was V1. Do you guys remember? This is V1, and this is V2. So if you adjust the way you're thinking about this and take a look at this point, that's where V1, that's when you scale V1 by 1. And then you scale V2 by what? By 0. And then so you have the weights 1, 0. So this is like a 1, 0 in your new special coordinate system. If I take a look at this point, then you're scaling V1 by 1 and V2 by 1. And then now you're at the weights 1, 1. And that's how you can describe your weights based on those vectors. And so if I randomly pick one over here, what's V1? V1 goes from here, it goes -1, -2. So it's -2 V1, and what's my V2? V2 goes over here positive, but I can go negative V2, so that's what that is. So I can use my weights to describe my new set of points. So now I have the point 1, 1, I have the point, oh, this is 1, 0, 1, 1, and -2, -1. So I can use that as my new set of coordinates based on these things. So that's kind of jumping ahead a little bit. So next time we're gonna take our matrix and apply it to the vector, and then we're gonna come up with this thing called the matrix equation. And then now we're gonna start, hopefully get comfortable with a matrix, a vector, and how that fits in with the system. And then after that, we're gonna take off with matrix and vector algebra. All right.